Hey, what's going on? This is the presentation for this class, and let's see what we got. And there we go. Just going. There we go. All right, awesome. So, problem 3.145. If y has a binomial distribution with n trials and probability of success p, find the MGF, the moment generating function. Let's do it. So, some relevant equations that I want to write down to start off with is the probability function for a binomial distribution. The binomial theorem that I found in Appendix 111, and also the moment generating function. You start off with mt equals the expectation value of e to the ty, and that is defined as the summation of e to the ty times the probability. Now, this is this is consistent for everybody. For whichever distribution you're trying to find. What you put in here for py, you could put in the py for a binomial distribution or a geometric distribution, or various other things. That's when the problem changes. So in this case, I'm actually taking my py, the one from here, and just putting it straight in and replacing that right here. All right, I'm going to gather the parts of the equation that are raised to the y. So if we look back in the previous one, I have e to the ty and also p to the y. Excuse me. What I have is n choose y, p to the et to the y, and then 1 minus p, which is also known as q, n minus y. If I compare that to the binomial theorem, I find that that is exactly what I have. I have all the components, and in my case, I have my n is the same as m for my previous, when I wrote down the binomial theorem. I have y is equal to I, and 1 minus p is my a, and p to the et is my b. So that being plugged into the binomial theorem, I can convert this to this. Here's the moment generating function for my binomial distribution. It's just that, p times e to the t plus q, where q is 1 minus p, all to the n power. And I'm done with that one. All right. So 3.4146 is asking me to use the moment generating function to find the expectation value and the variance. Here's a relevant equation. To find the expectation value, you simply take the first derivative of the moment generating function and evaluate it at t equals 0. So I need to find the ddt of this thing, and this was the moment generating function that I found in the previous problem. If I take the derivative, I need to make sure I keep in mind the chain rule. And then I plug in t equals 0. Plugging in t equals 0 will give me, well, I just plug in 0 for t. Done. Note that anything to the 0th power is 1. So this thing gets killed down to 1, and this thing gets killed down to 1. I have p minus p, so that's 1. So 1 to the, I simplify that. 1 to the anything power is 1. So that thing just kind of dies, and I have np. My expectation value is equal to np. And done. For the second part, they're asking us for the variance, and we basically use this general equation all the way around. The variance is equal to e to the y squared minus e to the y quantity squared. The e to the y squared can be found by taking the second derivative of the moment generating function and then setting that equal to 0. Since I already have the first derivative, I just simply need to take that derivative of the first derivative, and that will give me my second derivative. So what I have here to deal with is a product rule. And it gets a little bit complicated, but it's not really that bad. You just got to be careful. And then I evaluate it at t equals 0, and that pretty much kills everything over here. So this is e to the t, that's a 1, that's a 1, and then this would be a p minus, or p plus 1 minus p, so that would just be 1 to the n minus 2. But again, anything to the n minus 2, or 1 to the anything power is still 1. So that kills pretty much that part. So this is kind of what happens in the end after you evaluate for t equals 0. To get the variance, you simply plug in your answer for here and subtract off the square of the e to the y of the expectation, and so that would be the np squared. Simplifying that, I think I just distributed this thing into the parentheses, and simplifying some more and factoring out an np. This is my variance, which I think is what the rest of the is what the other way to calculate the variance. This goes along with what the variance for a binomial distribution is. Bear in mind that this isn't the easiest way to solve the problem of figuring out the expectation value and the variance, but it does show you a definite use for the moment generating function. If the moment generating function were something a little bit more complicated, finding the expectation value and finding the variance is simply a matter of taking the first and second derivative and evaluating at t equals 0. Once we have this, we're going to move on to another problem. Use the uniqueness of the moment generating function to give the distribution of a random variable with moment generating function mt equals blah blah blah. If I were to compare the moment generating function that I calculated with exactly what they have, you can see that this is, hey, that p is the same as 0.6 and that q is equal to the same as 0.4. Essentially, I look at this and I say, that has the same form as the binomial distribution, so this must be the moment generating function of a binomial distribution, because all of these moment generation functions are unique. So then I say, you can definitely see that this is the moment generating function for the binomial theorem, or binomial distribution, if p is equal to 0.6 and n is equal to 3. Plugging this information into our equation, the probability function is simply that. Your expectation value is np, as we proved earlier. And your variance of it is npq, which is 0.72. For problem 151, we want to, if y is has a moment generating function of mt equals blah blah blah, which you can tell has the form of a binomial distribution moment generating function, what is p of y greater than or less than or equal to 5? As you can see, this is the p is 0.7, the n is equal to 10, and the q is actually 0.3, but we don't have the, we don't need the q in our calculation. We can look up the number for in Appendix 2, Table 1, and if you look up the table specifically for n equals 10, and you set the p equal to or if you set the a is equal to 5, and you go down to the p is equal to 7, you're going to find out that the probability is 0.150. And that's it. I'm done. Thank you very much for listening to my crazy story.